In this video, we would like to introduce our paper at CVPR 2022, entitled Towards Robust and Adaptive Motion Forecasting, a Causal Representation Perspective. Forecasting motion trajectories of dynamics agents is critical for many intelligent systems, such as autonomous vehicles, social robots, as well as sports analytics. One common recipe to tackle this problem is to first design an encoder-decoder-based neural network, and then train it on a massive amount of data collected from various environments. This common practice has been working pretty well when the training and test data come from the same distribution. However, in real-world scenarios, we may encounter a wide variety of distribution shifts, where existing techniques still suffer from limited performance. Generally speaking, there are two common types of distribution shifts in the motion context. The first one is associated with spurious features, like agent density. During training, there might be some statistical correlations between the agent density and the future trajectory. For example, the higher the density is, the more likely the trajectory is nonlinear. However, these two variables are not causally related. As shown here, if the density grows due to extra agents behind or far away from the ego agent, the behavior of the latter should not be affected. Another common type of distribution shift arises from the change of motion styles, for example, the left or right hand traffic preference, which often has a strong influence on the motion behaviors. Given the variety of distribution shifts that may occur at test time, it is crucial for forecasting models to robustly generalize to novel situations of spurious features, and efficiently adapt to new motion styles. So how can we achieve this goal? In this work, we aim to promote the robustness and reusability of motion representations from a causal perspective. More concretely, we first introduce a formalism of motion forecasting through the lens of causality. Unlike previous methods that exploit all possible features, we split them into three different groups. First, the domain-invariant causal variables behind the physical laws, like collision avoidance, which should be universal to everyone at any place. Second, the domain-specific confounders that account for motion styles, for example, social distance. And third, non-causal spurious features, such as agent densities, as we discussed earlier. This causal formalism motivates us to treat each group separately. Our first goal is to remove spurious features for robust generalization. To do so, we propose to make effective use of the domain labels in the training dataset. Oftentimes, the training data is not collected from a single location but rather from multiple different environments. Previous work typically merges them into a larger one, for instance, the notable ETHUCY datasets. However, each subset is often inherently different. A model trained to minimize the prediction errors averaged over all training examples regardless of their sources, may not only absorb some selection biases in the training data, but also overlook the robustness across environments. To address this issue, we propose to train the model with an additional loss penalizing the variations of prediction errors across environments. This regularizer encourages the model to be equally optimal in all environments, including both the ones seen during training as well as those unseen at test time. However, the invariant regularizer alone comes with a clear drawback. The learned representation tends to not only remove the spurious features but also drop the motion styles that may sparsely change across environments. To tackle this problem, we further introduce a modular architecture, which factorizes the knowledge of invariant and style features for efficient adaptation. More specifically, we introduce a second encoder, which takes as input some scene observations and outputs the corresponding style features. We then inject the style features into the invariant part through a style modulator in the form of a residual block. This modular design allows us to precisely pinpoint a small subset of parameters for adapting the model across different styles. However, training such a modular network is not trivial. To enforce the knowledge structure, we introduce a style contrastive loss for pre-training, which encourages the model to produce an embedding space that can capture the style relations. Since the contrastive task does not impose any prior assumptions on the number of classes, it is particularly suitable for knowledge transfer to new motion styles. Another advantage of this design is that this auxiliary loss can be used as a self-supervised signal at test time for online refinement. We validate our method on several datasets and obtain strong results for both zero-shot generalization and few-shot transfer. For more details, please check out our paper and code. Thank you for your attention.